subject of all time. Okay, so a lot of what we're going to talk about is review from Chemistry 1 in this section, just like a lot of things have been so far this chapter. But we're going to get to something called Coulomb's law that basically explains how everything works in the realm of subatomic particles and how things are bonded together and all these things. And there's an equation for it, but you don't actually ever do any math. And so it's very important to know for the AP exam to explain things according to Coulomb's law. So we will probably, before our test on that extra day next week, in between the quiz and the test, we will probably focus on hitting home with that, okay? But first, the modern atom. Atoms and molecules can be identified by their electron distribution and energy. So recall from Chem 1 that the simplest view of the atom is that it consists of a tiny nucleus and electrons that move about the nucleus. Remember that it was originally theorized that the electrons moved in a circular orbit, then it turned into an electron cloud, and now we have things called sublevels that are where the electrons are located. But the nucleus, and then there's the electron cloud around it. And the nucleus has most of the weight in the atom. So if you look at the relative masses, or the actual masses of each of the subatomic particles, the proton and neutron have the same mass, and the electron is a lot smaller. So we say that the nucleus is where the mass is from any atom. Okay? Anybody remember what do you call it when you add the number of protons and neutrons together?
Atomic number.
Adding our mass.
The mass number.
That was close.
The atomic number is the number of protons.
Oh.
Or electrons in a neutral atom. Yeah. So if all atoms are composed of these same components, why do different atoms have different chemical properties? It all has to do with the arrangement of the electrons. Atoms behave differently because of the arrangement of their electrons. Even though the nucleus has all the weight, the electrons take most of the volume of the atom, and then they are able to intermingle with different atoms, and by those interminglings, we form molecules. As a result, the atoms of different elements, which have different numbers of protons and electrons, show different chemical behavior. So if we look at sodium's atomic number is 11, so it has 11 protons in the nucleus. Because atoms have a net charge of 0, then that means that at a neutral atom, the number of electrons are equal to the number of protons. So for a sodium atom, it has 11 protons and 11 electrons. This is always true for sodium. However, the neutrons can change. Isotopes are atoms with the same number of protons but different number of neutrons. I feel like we mentioned that before, like last week, but just a refresher what isotopes are. Okay, so here's a picture of our sodium atoms. I know it's kind of hard to see, but this has the top number is the mass number, and the bottom number is the atomic number. And the mass number is the protons plus the neutrons. There's nothing on there about electrons. There's nothing on there specifically about the neutrons alone. Okay? But then with this isotope in the nucleus, we have 13 neutrons, so the mass number is different, but the atomic number stays the same. And the number of electrons stays the same as well. How do you think how do you know when it's changed the number of electrons? What do you think it shows? It could be a different element, but what if it was sodium and we wanted to show that it had different number of electrons? It would be an ion. Yeah, so it would have a charge, and that would show you that the electrons are different. So for a neutral atom that has an atomic number of 9 and a mass number of 19, how many electrons and how many neutrons does this atom have? Okay, well, does anybody want to take a guess at what element it is if it has an atomic number of 9? Fluorine. Right? If you look at number 9 on the periodic table, that's fluorine. Okay, and we know the atomic number is 9, and we know the mass number is 19. Okay, so we know that it has 9 protons. How many electrons does it have? 9. Since it's neutral, it's just an atom, it's the same as the atomic number as well. So it's also 9 electrons. And then the neutrons, you would take the mass minus the atomic, which would give you 10. Okay, so that's how you do this example. Now, even though I didn't really say it, but we kind of led to it, let's say that instead of a neutral atom of fluorine, you had the fluoride ion. So what if it was like 19, 9, but then it was F with a -1? The protons would be the same, they'd still have 9. The neutrons would still be 10, but how many electrons would it have? 10. Because when it's a negative, that means you gain 1 electron. You added 1 electron to make it more negative. Okay? So this one, that is telling you that the electrons don't equal the protons when you see that charge there. That might be like you might see that on the AP exam. So just to kind of review that and or talk about it for the first time. It's good. Okay, Coulomb's law. Here we go. I will try to do my best. At Coulomb's law. This is actually from chapter 8. So now we're getting into a chapter we haven't seen yet in this unit in our book. So the energy of interaction between a pair of ions can be calculated using Coulomb's law. Now this is the equation that's associated with Coulomb's law, where E has the unit of joules, J for joules. R is the distance between the ion centers in nanometers, and Q1 and Q2 are numerical ion charges. If you were going to get into very high level chemistry, you might actually solve for this equation for different numbers. We are not going to do that in AP chemistry. We need to know the effects of Coulomb's law, not any numerical answers for Coulomb's law. Okay? So we can use a Coulomb's law to calculate the attractive force between oppositely charged ions. The energy will be negative when it indicates that an ion pair has lower energy than the separated ions. If you were to calculate. So if I'm not going to have you calculate it, maybe I give you a value and it's a negative number. And so if it's a negative number, then that would show you that there's lower energy when the ions are paired together than when they're separate. So usually some things like to have low energy and some things like to have high energy. So this helps predict whether they will bond together well. Okay? Coulomb's law can also be used to calculate the repulsive energy when two like-charged ions are brought together. So in this picture, these are all diatomic molecules from our Hunkel fiber list, and they all have the same charges, right? Because technically, chlorine and a chlorine both have the same charge. But those are not bonded together by their ionic bond, but they're bonded together from a covalent bond. But their electrons are still being shared in that covalent bond. So Coulomb's law could also calculate that too. So in this case, the calculated value would be positive if you were to have two like-charged ions brought together. The attractive force between any two ions is governed by Coulomb's law in these ways. The force is directly proportional to the charge of each ion and inversely proportional to the square of the distance. Yeah.
What would the value be for the last one?
Positive. It's okay. So these 2 points right here are really what you're going to use as reasoning to help explain yourself using Coulomb's force as an example. Okay? For ions of a given charge, the smaller the ion size, and thus the smaller the distance between the ion centers, the stronger the Coulombic force of attraction, and the higher the melting point. Ions with higher charges lead to higher Coulombic forces and therefore higher melting points. about ion size, do you guys know that, like, if you look on the periodic table, this is a trend. We're going to talk about periodic trends this chapter, but it's all based on how the nucleus, positive nucleus, pulls the electrons towards itself. And the more protons and neutrons you have in the nucleus, and the more electrons outside of it, it's just going to get bigger and bigger because you have more. Okay? The size of an anion, is a lot bigger than the size of a cation, and that's because anions have more electrons, so their radius, where the electrons are, their electron cloud, makes them larger. Even if there's something called an isoelectronic, where they have the same number of electrons, the cation is always bigger. So when you have a smaller ion, so that there's less distance between the two nuclei of each of them, the Coulombic force will hold them together, and because they're being held together by stronger forces, it'll have a higher melting point, meaning it's going to take a lot more energy to break the bond that's holding them together to make it go from a solid to a liquid. Okay? This is what AP chemistry is all about, talking about these bonds and how do you break the bonds and how strong are the bonds. Okay? And if you have higher charges, so comparing like a +1 - 1 compound compared to a +2 - 2 compound, the more electrons you have transferring over because of higher charges, that makes them stronger. So a compound with +2 - 2 will be stronger than a +1 - 1 compound. So like if we had like sodium chloride versus the like magnesium oxide. Sodium's a +1, chloride's a -1, magnesium's a +2, oxygen's a -2. The forces inside of the magnesium oxide are stronger because even though, well, these are isoelectronic, these are not isoelectronic. These are stronger because of the +2 - 2 charge. Does that make sense? So the higher charges you have, the stronger it will be held together, the harder it will be to break the bond. Okay? We'll talk about that isoelectronic thing soon. That's a good thing to know. At some point we'll cover it. But, yeah. Okay. When you have the identical atoms, so like the Hunkel fiber list, looking at the energy terms when two hydrogens are bonded together or brought close together, there are two unfavorable potential energy terms: proton-proton repulsion and electron-electron repulsion. So remember, we know opposites attract, the same things repel each other. So if you have the electrons coming towards the electrons, they're not going to interact well. Or if you have the protons from the nucleus coming with the protons of the other nucleus, it's not going to interact well. So in order for it to be favorable, you have to have the electrons of one being attracted to the protons of the other. So this picture is from the textbook, but it's trying to show how they can move together to make something favorable. So what happens when they're favorable? Instead of two separate atoms, they will tend to form together to achieve the lowest possible energy. So that means that a bond will form if the bond lowers the total energy of the process. And that happens for all that are on the Hunkel fiber list. That's why they are diatomic molecules, because they have less energy together than if they were to stay separate. So that's why we don't just find like random oxygen atoms by themselves. Oxygen's always paired up with another oxygen. Okay? So when you have the lowest total energy, it minimizes the repulsive and attractive energy terms. And this distance, when the energy is minimal, is also called the bond length. So this is something that you could get into with, and they measure it in either nanometers or something that starts with an A that I can't remember right now. But that's where we get into bond length. Okay, so now I have this graph on the next slide that's in your notes. where it's trying to show you where the energy lies. So far to the right, the two hydrogens are by themselves. They're separate. Far to the left, they are really close together. I know it's hard to tell, but this set is closer together than this set is. Okay, and that shows by the internuclear distance, where they're closer together here than right here, and then as you continue farther right on the x-axis, it will spread more apart. Okay, and then the y-axis is the potential energy, where when they're separated, that is 0 energy, but the lowest energy is when they have this bond length of 0.074 nanometers, and that energy is negative 458 kilojoules per mole. Does anybody remember when it's negative? Is it endothermic or exothermic? It's exothermic when it's negative because it's exiting. So that tells us that it would lose 458 kilojoules per mole of hydrogen molecules. So we can say, I think this is coming up, this is next. We can say that a bond is formed between the hydrogen atoms. We mean that the H2 molecule is more stable than two separate hydrogen atoms by a certain quantity of energy. So that's what that negative 458, that's how much energy it's more stable than when they're separate from each other. So that's how we get into bonding, is what's the most favorable terms, what has the lowest energy, the distance between the subatomic particles, all of that plays into this with the Coulombic forces. Okay, so we'll talk more about that another day. Okay, Niels Bohr, I think his birthday is sometime in August, I don't remember. He was the guy who came up with a quantum mechanical model for the hydrogen atom, and he first proposed that the electrons move around the nucleus in circular orbits that are all concentric, and he calculated the radii for these. And it worked out amazingly well for hydrogen, but then it didn't work for anything else. So this is a picture of what his model looks like. N stands for energy level, and then the distance from the nucleus. We now know that they're not perfectly segmented away. That he thought is like rungs on a ladder, and everybody had the same distance away, and it just kept getting farther and farther away. But we now know that the energy levels have different amount of spacing, and so that was one way that his model is proved wrong. They also tell us, this is the line emission spectrum from EMR, visible light, that we talked about in Chemistry 1. We'll talk about that another day too. But the most important thing to come from Bohr's model is the energy level available to the electron, which is this equation, where n is an integer describing the orbit radius, and z is the nuclear charge. Bohr is able to calculate hydrogen atoms' energy levels that exactly match the values obtained by experimental. So that's why it works so well for hydrogen, because everything mathematically was fitting the test. Remember from Chemistry 1, when an electron is in the lowest energy state, where it's in the lowest energy level of 1, it is said to be in ground state, like a ground hamburger, right? And then when it's not in ground state, it's called excited state. But Bohr wasn't perfect, because at first it appeared promising, but after he tested other things besides hydrogen, it did not work out well. So because of this, we concluded that Bohr's model was fundamentally incorrect, and that we have come up with better models for now. So although Bohr paved the way for the current atomic theory, it's important to realize that the current theories are in no way derived from the Bohr model. We found other data to support them and other means. So you should know that electrons do not move around the nucleus in circular orbits. One of the new sublevels is shaped spherically, but it's only one. This is a review of Chemistry 1. We talked about the off-law principle, electron configuration, quantum numbers, that kind of stuff. So The quantum mechanical model of the atom shows where the electrons are arranged in hydrogen-like atomic orbitals, and we can also use it for other things besides just hydrogen. So Bohr was wrong because he could only use hydrogen. Okay? So our main assumption here is that all atoms have the same type of orbitals as described for the hydrogen atom. As protons are added one by one to the nucleus to build up elements, electrons are similarly added to these hydrogen-like orbitals. This is called the Aufbau principle. If you have one of those handouts from Chem 1, the arrows, the lines, is the Aufbau principle. The way that it's filled in. Okay? Does anybody remember quantum numbers? It's okay if you don't. You're not tested on them. You just kind of need to know stuff about them. In atoms and ions, electrons can be thought of as being in shells and subshells, as described by electron configuration. Shells are also known as energy levels, we called them last year, where the n quantum number, and we have 7 energy levels because there are 7 rows on the periodic table. Okay? Subshells are also known as sublevels and orbitals, where the L quantum number that describe the shape of the area in which the electron could be located. Okay? And we had lots of different shapes, but it's important to note you won't be specifically asked about quantum numbers or have to tell me the quantum numbers for any given problem on the AP exam. Okay? But the background information is vital. So when I say energy level or shell or sublevel or subshell or orbital, this is where it comes from. Okay? So in example 12, we are going to fill in the orbital diagrams for these elements. And the way that we fill it in, we did this in Chem 1, is by drawing arrows to represent electrons. And each line can hold 2 electrons that have opposite spin. So one up, one down. Okay, well, maybe when we start this you'll remember. Okay, so how do we know how many electrons something has? The atomic number. If it's neutral, it's just the atomic number. So how many electrons does hydrogen have? 1. So the first electron just gets filled in into the 1s. And you could do a half arrow like that, or you could do a full arrow pointing up. Okay? Now, next is helium, and that has 2 electrons. So we'll put the first electron pointing up, and then the second electron goes in the same line, but it points down. Is this coming back to people? Yeah. Okay. So the Pauli exclusion principle tells us that the electrons have to have opposite spins when they're paired together, and each orbital must be filled before moving on to the next highest. So that's why we put the second arrow on the 1s. Now, if we go to lithium, and that has 3, we would go 1, 2, and then the third one can go in the 2s. Okay? And then beryllium has 4, so that would be 1s2, 1s2, and then 2s2, like that. My arrows look horrible. I apologize. Okay, when we get to the p orbital, or the p sublevel, subshell, what other word? This one is one where it was Hund's rule, where it acts like a teeter-totter, where you have to put 1 in on each line before you go back and put in another one. So since we only have 5 for boron, it would go in the first pointed up. If we were to do carbon, which would be next on the periodic table, the next electron would go here on this line. Okay? And then nitrogen, the next electron would go here. And then we would go back and fill in the second before moving on to 3s. Does anybody remember that? Maybe? Hopefully? Okay. I don't know if you would really have to do this on the AP exam, but it's good to visualize for electron configuration. So we reviewed it. Okay. At this point, it's important to review the concepts of valence electrons. The electrons in the outermost principal quantum of an atom. Outermost energy level, outermost shell. Yes. So, does anybody remember how do we find the valence electrons on the periodic table? Like, how do I know? Like, if I say, how many valence electrons does chlorine have? How would you know?
It has 1.
would be minus 1 would be the charge. What is an ion? It's what column it's in. So the valence electrons, most of the time, can be found on the periodic table if it's in columns 1A through 8A. So like hydrogen, beryllium, boron, carbon, nitrogen, oxygen, fluorine, helium. Those columns, well, except helium. How many does helium have?
2.
2. It's a trick question.
Why do I know that?
I don't know, but it's good. So those are where you can find them. We're going to see where do we find them in electron configuration in a second. But anything that's not a valence electron could be called a core electron. Okay? Just to refresh your memory. So remember that, oh, I guess this is in here. Sorry. The elements in the same group or vertical column have the same valence electrons. So again, this is 1 valence, this is 2 valence, 3, 4, 5, 6, 7, 8. If you want to write this down on your periodic table, that's fine, because we'll use the ones I give you during tests and quizzes. So it's yours to write stuff down if you need to. Okay? And this also, the reason why they have the same amounts of valence electrons, they're grouped this way, but they're also grouped this way because of their similar properties that Mendeleev saw as he organized his periodic table. And that's one of the reasons why we have the shape we have for the periodic table. Okay, so also from this shape, remember that the first 2 columns make up the S area. This is like the ends with side of your handout from Chemistry 1, if you have one. And then over here is the P block, because they all end with a P orbital. The helium technically fits in over here, because there's only 2 electrons. And then the D block is 10 across, right here. And then the F block fits in after the 6S and the 7S. You have 4F and 5F. Okay, so because you're not allowed to use a handout, you need to learn, if this was not how you did it before, you need to get comfortable with just recognizing the shape and working your way through electron configuration. Okay, and the way you do that is you always start up in 1s, and you always fill the orbital or the subshell or the sublevel, whatever you want to call it, before you move on. So, like you would go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. The thing that gets people the most is that like 3d is after 4s. I can post the song from Chemistry 1 online if you want to get that song stuck in your head. Again, 1s2, 2s2, 3s2. Yeah, whatever. I didn't think right. Oh yeah, we did. Woo! 3d10. Yeah. Woo! Yeah, you did. You saw it. You were just not paying attention. You're just not paying attention. Okay, so let's go ahead and write the long electron configuration for each of these elements. Okay, and I only put 2. If you need more help, we have a worksheet on this. If you need more help on this stuff, I can help you. But I just did 2 because I thought hopefully it'll come back to you as we go. Okay, and I would strongly suggest, unless you want to memorize the arrow side of the handout, I would strongly suggest looking at just a periodic table and working your way through that way. Here's one. Okay, so the first one we have is K. What's K stand for? Potassium. And how many electrons? 19. So total electrons are what we're doing here. Okay, so starting up in the first row, the first thing you use is 1s. And s's hold how many? 2. Okay, you don't have to put commas or anything like that. Then after 1s, then we have 2s2. Which part do you know, like how many electrons you've written down so far? What do you look at? The exponents. Yep, these right here will tell you how many electrons you have filled. So we have 4 electrons filled. We need 15 more. Next will be 2p6. Then 3s2. 3p6. And 4s1. Another thing that if you want to write this on your periodic table, you can. Over here on the side, since there are 7 energy levels, 7 shells, you can write next to hydrogen 1, then next to lithium 2, 3, all the way down. And that might help you remember that when you get to potassium, that's in the 4th row, so that will be 4s. You know, if you want to write that down. Okay.
Yeah, can you do the whole S? 'Cause I don't really understand.
The F's come in after the S, the 6s and the 7s, and the F's are 4f and 5f. 14 across.
And that was going before the like 5D2, so
Yes.
Like 4F14 then 5D2.
Yes.
Okay.
Mm-hmm. Okay. Now, to point out where the valence electrons are in here, okay, we can see valence electrons from electron configuration. Valence electrons are in the outermost energy level. So, looking at the first number, that is the energy level, or the shell, that the electrons are located in. So, what is our outermost energy level? 4, from the 4s, right? So, in the 4s, this is our valence electron. Sorry, it's hard to read that. But, so we have 1 valence electron, because there's 1 electron located in the 4th energy level. Which, we said, column 1a has how many valence electrons? 1. That's where it comes from, right there. So you just generalize 1a, 1 electron, but it's from the electron configuration. Okay? So let's do P. What's P? 15. It's phosphorus. Yep. Okay, so it's going to be shorter than what we just had, right? So we have 1s2, 2s2, 2p6, 3s2, and 3p3. How many valence electrons do we have this time? It's all of them in the highest energy level. So we have 3s and 3p, both in the 3rd energy level, which is our highest energy level. So if we have 2 plus 3, it's a total of 5 valence electrons. So these right here are all the valence electrons for phosphorus. And if you count it across, phosphorus is in 5a. So that makes sense. Okay. What gets weird with the valence electrons in electron configuration is when you have the transition metals, because you have 4s and then 3d. The valence electrons actually come from the 4s, not the 3d part of it, because 4 is higher than 3. But yeah, that's just like a trick question. Okay, now if you are comfortable just doing the long way of writing electron configuration, that could be what you do. It's fine. But you do have the option of doing the noble gas way. The noble gas way involves writing a part of the configuration as replaced as a symbol of the noble gas, and then after the noble gas is positioned, then you fill in the rest of the way. So it's up to you. Either one is perfectly fine to use. If just writing out the long way is what you want to do, that's fine. Okay? So you always pick the noble gas that's closest, but does not go over the number of electrons you need. And then you don't include anything from the noble gas, just what comes after the noble gas until you hit that element. Okay? So let's do the phosphorus just so you can see. We already did that one, right? Which noble gas is closest to 15 but doesn't go over 15? Neon. Remember, you have to pick from the noble gas column, which is AA. You can't pick from anywhere else. So neon is Ne. So you just write Ne in brackets. Some people like to put the number of electrons in there. You can, but you don't have to. And then, so neon is in the 2nd row down at the end of the P block. So that would be 2p6. You don't write anything down before 2p6. You just jump ahead to 3s2 and then 3p3. The point of noble gas configuration, besides just saving time, is to show just the outermost energy, the outermost electrons, whether they're valence or not. So this is a quick way to see that, oh, I've got 5 valence electrons because that's the highest energy level that we hit, sort of thing. And that's a way that noble gas helps you see those valence electrons. Okay? So last one we have Ca. How many electrons? 20. Okay, what's the closest noble gas? Argon, Ar. Okay, and that has 18, right? And so that is the third one down, so that would be 3p6. And next would come 4s2. And remember that with the ends with periodic table, if you know that calcium is the second one in and the 4s row, then like that also helps you figure out where you stop. So calcium has how many valence electrons? 2. So that shows you that. Okay? This is where we don't stop. Just kidding. We're not done with 1.5 yet. But we're going to keep talking. So, okay. Another way that the periodic table is grouped together, it's good for us, is that it shows trends in the way that the periodic table is arranged. So we have atomic trends for that. Ionization energy is one trend that we see. Ionization energy is the energy required to remove an electron from a gaseous atom or ion. So this equation just shows how this is the atom that's neutral, and then it has become positive because you lost an electron. Okay? So the atom or ion is assumed to be in its ground state from the ionization energy. This chart, is this in your notes? Yeah. So there are sometimes more than one electron that you can lose, and so it's important to see that if you have more than one electron to lose, there are different energies associated with losing specific electrons. Now, where it has the stair-step line and it says core electrons, that means it's going to take a lot more energy to lose a core electron than it is to lose a valence electron. Okay? Valence electrons are what you like to lose. Core electrons you don't want to lose. So that's why, do you notice how, like, for sodium, the first electron, or the first ionization energy to remove that first electron, its valence electron, is only 495 kilojoules per mole, but then the second ionization energy to remove another electron is 4,560. So that's a huge jump, meaning, since it's a huge jump, it doesn't want to lose more than one electron, basically. Okay? When you are in AP chemistry, you can't just, like in Chem 1, we would say, like, okay, which one has higher ionization energy? And you see, like, oh, the largest is fluorine, because it doesn't want to lose electrons, it wants to gain electrons. So then we would, like, see which one's closer to fluorine, and then that's the way we pick it. That's not really what we do here in Chem AP. So sometimes you're given numbers associated with it, sometimes not. But you see how fluorine, we said in Chem 1, has the largest ionization energy, which makes sense compared to all of the other numbers in the representative elements. But the noble gases are even higher because they're very stable and they don't want to react at all. And the cations are very low because they want to lose electrons. Excuse me. And the anions are very high because they don't want to lose, they want to gain. Okay? So what you might do is you might look at the values and think about electron configuration and Coulomb's law to explain these things. Okay? So the ionization energy for phosphorus is 1060 kilojoules per mole. Ooh, that's a typo. And that for sulfur is 1005 kilojoules per mole. Why? So why do you think that phosphorus has a higher ionization energy, so it needs more energy to pull electrons away than it does for sulfur? Use electron configuration and Coulomb's law to explain. So I have the answers here. The first one I have to talk about is the electron configuration. So with electron configuration, phosphorus has 15 electrons, sulfur has 16 electrons, right? So for phosphorus, the valence electrons are 3s2 and 3p3. For sulfur, the valence electrons are 3s2, 3p4. When we did this orbital notation, we didn't get this far, But this is the orbital notation of the, which I know the 1s, the 2s, and the 2p don't match, but this would be like 3s2 and 3p4 there. Because you have this fourth electron in the 3p, making it unbalanced, it's a lot easier to lose that fourth electron because the teeter-totter is shifted and not balanced correctly. So that's why, that's one reason to prove why sulfur has a lower value. Because since the 3p orbital is uneven, because it has that fourth making it uneven electron, it's easier to lose that extra electron. Does that make sense when you see it like this? And remember our teeter-totter rule about making things even? Okay. Some people would say, well, it's closer to fluorine, so it should have a higher number. And so this is just like one of those ways that there are exceptions to the general trend. Okay. The other way to explain this with Coulomb's law, I have it pop up in a second, so do you guys need this anymore? Okay. If you need to rewatch this again, once I get it online, you can always come back and rewatch it if you didn't understand it the first time, or talk to me. Okay. Do you remember Coulomb's law yesterday? We talked about there's that equation, but we don't actually solve the equation. We just use it to explain. It all has to do with the interaction of the nucleus, the protons in the nucleus, and the electrons on the outside. Okay? So, for Coulomb's law explanation, sulfur, not only does it have an extra electron, but it also has an extra proton. So by having an extra proton, it has a nucleus that is slightly larger than phosphorus. And it creates, with that extra electron, also a larger atomic radius in general. So when you have a larger atomic radius, so the electrons are farther away from the nucleus, it's easier to lose electrons that are farther away. So since it's easier to lose electrons that are farther away, it needs less energy to get that electron gone. So this is another reason why the number is lower. Okay. On an AP free response question, I think that they would accept either one of these responses as a valid reason why it is the way that it is. But this is something that a lot of times we think chemistry is a lot of math related, and that's how I push it in Chem 1. But you have to explain this kind of stuff on the AP exam, and you have to dive more into it, more than just the math.